While artillery shells and missile strikes dominate headlines from Ukraine, an equally critical battle rages across the electromagnetic spectrum. Since February 2022, Russian forces have deployed sophisticated GPS jamming systems across the front lines, creating electronic warfare bubbles extending up to 80 kilometers from their positions. But what's received remarkably little attention is how Ukrainian forces have adapted by embracing dual-frequency GPS technology, a capability once restricted to military applications but now available in consumer electronics. This is the story of how smartphone technology and ingenious engineering are rewriting the rules of modern warfare. The conventional understanding of warfare focuses on physical weapons, but in Ukraine, an equally decisive battle is being fought in the electromagnetic spectrum. Russian jammers flood the L1 frequency band at 1575.42 MHz with noise, effectively blinding standard civilian GPS receivers used in Ukrainian drones and intelligent munitions. These electronic warfare bubbles extend up to 80 kilometers from Russian positions, creating vast areas where conventional GPS navigation fails completely. The Russian military planners anticipated that this electronic warfare superiority would neutralize Ukraine's drone advantage, potentially crippling their reconnaissance and precision strike capabilities. This invisible battlefield has become just as crucial as the physical one, with electromagnetic dominance potentially determining the outcome of ground operations. Recent field reports from Ukrainian drone operators reveal a remarkable adaptation. Approximately 73% of their custom-built reconnaissance drones now incorporate dual-frequency GPS receivers. Unlike standard receivers that process signals on the L1 band only, dual-frequency receivers simultaneously track both L1 and L5 bands at 1575.42 MHz and 1176.45 MHz respectively. This technological distinction has proven critical in contested environments. The newer L5 signal, operational only since 2020, uses a frequency range that many legacy Russian jammers cannot effectively disrupt. Ukrainian engineers discovered they could maintain positioning by prioritizing the L5 signal when L1 becomes compromised. This adaptation has preserved their ability to conduct precision reconnaissance, target acquisition, and battle damage assessment, functions that form the backbone of modern combined arms operations. What was designed to be a crippling Russian advantage has been significantly neutralized through this technological countermeasure. Dual-frequency GPS technology offers multiple advantages beyond simply avoiding jammers. These systems can detect and mitigate multipath errors, signal reflections off buildings or terrain that confuse single-frequency systems. This capability has proven essential for precision operations in urban combat zones like Bakhmut and Avdiivka. Additionally, the L5 signal uses a more sophisticated signal structure with higher transmission power and bandwidth, making it inherently more resistant to both unintentional interference and deliberate jamming. According to a technical assessment published in April 2023 by the Ukrainian Defense Technology Institute, dual-frequency systems maintain positioning accuracy within 3 to 5 meters even when subjected to jamming power 30 times greater than what disables conventional receivers. These receivers also utilize advanced error correction algorithms that automatically compare timing discrepancies between the two frequency bands to detect and discard corrupted data. This ionospheric error correction capability, originally designed for surveying applications, has reduced positioning errors by up to 60% compared to single-frequency systems, even in areas without active jamming. Perhaps most remarkable is the source of this technology. Rather than relying on expensive military-grade components, Ukrainian volunteer groups like Aerorozvidka have repurposed dual-frequency GPS chips from consumer smartphones and sports watches. The Broadcom BCM 47755 and U-Blox F9 chipsets, designed initially for enhanced urban navigation in smartphones, have become critical components in the Ukrainian drone fleet. In interviews, a volunteer engineer identified only as Serhiy described how his team extracts these chips from donated Samsung Galaxy S20 phones and Garmin Fenix 7 watches and integrates them into custom circuit boards for drone navigation systems. This repurposing effort has created a supply chain largely immune to export controls and sanctions. What was designed for civilian navigation in crowded urban environments has become a crucial military asset, demonstrating how commercial technology can be repurposed to counter sophisticated military systems at a fraction of the cost. As one Ukrainian drone operator noted, sometimes the best military technology isn't military technology at all. The technical challenges of integrating dual-frequency receivers into existing drone platforms extend far beyond simply swapping components. Ukrainian engineers have developed sophisticated firmware modifications that fundamentally alter how positioning data is processed and prioritized. Their custom algorithms implement what they call jamming-aware navigation systems that continuously monitor signal quality across multiple frequency bands and satellite constellations. When jamming is detected, these systems dynamically shift their reliance between GPS, GLONASS, Galileo, and Beidou constellations while adjusting the weighting of L1 versus L5 signals. This adaptive approach ensures maximum positioning reliability under varying electronic warfare conditions. Some advanced implementations even incorporate inertial measurement units salvaged from smartphone components to provide dead reckoning capabilities during brief periods of complete signal loss. The integration extends to power management as well. Dual-frequency receivers typically consume 20 to 30% more power than single-frequency counterparts, a significant consideration for battery-powered drones with limited flight time. Ukrainian engineers have developed pulse scheduling algorithms that temporarily reduce positioning update rates during straight-line flight, then increase sampling frequency during critical navigation phases such as waypoint transitions or landing approaches. The adaptation hasn't gone unnoticed by Russian forces. Captured Russian documents from March 2023 reveal orders to upgrade their R-330 Zhtel electronic warfare systems to target the L5 band, acknowledging the effectiveness of Ukraine's technical workaround. This has triggered an accelerating electronic cat-and-mouse game between Ukrainian engineers and Russian electronic warfare specialists. The Russian military, which initially held a significant advantage in electronic warfare capabilities, now finds itself in a reactive position, trying to catch up to Ukrainian innovations. This represents a profound shift in the electronic warfare dynamic that existed at the beginning of the conflict. What makes the Ukrainian adaptation process remarkable is its accelerated timeline compared to traditional military procurement cycles. While conventional military development might require years to field new counter-jamming technologies, Ukrainian volunteer engineers have implemented solutions within weeks of identifying vulnerabilities. This agility stems from their willingness to accept good enough solutions and iterate rapidly, a stark contrast to the exhaustive testing regimes of established defense contractors. This technological improvisation represents a profound shift in modern warfare, the democratization of capabilities once exclusive to major military powers. Military analysts from NATO countries are closely studying Ukraine's improvised dual-frequency solutions as a cost-effective counter to sophisticated jamming systems. The Pentagon's Defense Innovation Unit launched a program in January 2023 specifically examining commercial dual-frequency technologies for potential military applications, directly citing Ukrainian battlefield innovations. The lessons from Ukraine's dual-frequency adaptation will likely influence military doctrine and equipment design for decades. The demonstrated vulnerability of single-frequency systems has prompted several NATO countries to accelerate plans for upgrading navigation systems across their inventory. More profoundly, Ukraine's success challenges conventional assumptions about the relationship between technological sophistication and military effectiveness, suggesting that adaptability and integration often matter more than raw technological superiority. The implications extend well beyond the military sphere. Manufacturers of precision agriculture equipment, autonomous vehicles, and survey instruments are accelerating their transition to dual-frequency receivers based on lessons from Ukraine. According to recent industry reports, the global market for dual-frequency GNSS chips is projected to grow from $1.8 billion in 2022 to $4.3 billion by 2026. What began as a battlefield adaptation is now influencing civilian technology development worldwide. The proven performance of these systems under the most challenging conditions possible, active electronic warfare, has demonstrated their value for civilian applications requiring high reliability. Industries from autonomous transportation to precision agriculture are now implementing technologies tested in the crucible of combat. This represents an unusual reversal of the traditional flow of technology from military to civilian applications, with battlefield necessity driving innovation that will eventually benefit civilian users worldwide. The dual-frequency adaptation represents just the beginning of what military technologists call countermeasure development. Ukrainian engineers are already exploring next-generation solutions as Russian jamming systems evolve to target both L1 and L5 frequencies. These include experimental work with triple-frequency receivers incorporating the L2 civil signal at 1227.60 MHz, creating systems capable of maintaining positioning even when two frequency bands are compromised. More ambitious projects involve mesh networking capabilities that allow swarms of drones to share positioning data, effectively crowdsourcing navigation information across multiple platforms. If several drones in a swarm experience different jamming effects, their collective positioning solution remains robust through distributed computing approaches. This collaborative navigation concept represents a fundamental shift from platform-centric to network-centric electronic warfare resilience. As the electronic contest continues to evolve, Ukrainian engineers maintain their innovative edge through rapid iteration and willingness to embrace unconventional solutions. Behind the technical specifications and electronic countermeasures lies a profoundly human story. The Ukrainian adaptation to Russian jamming represents not just technical ingenuity but a national characteristic of resourcefulness under extreme pressure. Volunteer engineers, many former software developers, electronics hobbyists, and telecommunications professionals, have created an innovation ecosystem that operates with remarkable speed and effectiveness despite limited resources. Their work often takes place in makeshift workshops, sometimes in buildings without reliable power, occasionally within range of artillery fire. The motivation driving this innovation isn't profit or professional advancement, but national survival. This human element explains why Ukraine has been able to maintain technological parity or advantage in specific domains despite Russia's vastly larger defense industrial base and longer military tradition. The Ukrainian approach to electronic warfare adaptation demonstrates how necessity, ingenuity, and determination can overcome seemingly insurmountable resource disparities in modern warfare. The electromagnetic battle in Ukraine represents a fundamental shift in modern warfare. What began as a significant Russian advantage in jamming capabilities has evolved into a sophisticated technological contest where Ukrainian ingenuity has effectively neutralized much of Russia's electronic warfare superiority. By repurposing dual-frequency GPS technology from consumer devices, Ukrainian forces have maintained their critical drone reconnaissance and targeting capabilities despite intense Russian jamming efforts. This adaptation demonstrates how commercial technology, creative engineering, and rapid innovation cycles can overcome traditional military advantages. The implications extend far beyond this specific conflict, influencing future military doctrine, defense procurement, and even civilian technology development worldwide. The dual-frequency revolution in Ukraine proves that in modern warfare, adaptability often trumps raw technological superiority, and that solutions to complex military problems might be found in the most unexpected places, like the GPS chip in an ordinary smartphone. As electronic warfare continues to evolve, the lessons from Ukraine will shape how militaries worldwide approach the invisible but crucial battlefield of the electromagnetic spectrum for decades to come. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.